Hello, this is Brian Washburn. I'd like to introduce velocity and acceleration in cylindrical coordinate system. Before I do that, what I'd like to do is first review Cartesian's acceleration and velocity in a Cartesian coordinate system, and then we're going to look at cylindrical coordinate system, and then eventually we'll look at spherical coordinate system. Part of the reason why we want to do this is because certain problems, the geometry, solving the problem may need to use a cylindrical or spherical system. It might make the problem easier, okay, by doing that. And so let's first introduce, how do I represent the position of a particle? Obviously, I'm going to start with my Cartesian coordinate system at x, y, and z, and those guys are fixed in time associated with the component. So if I have a mass m, I can always represent the point of that mass in space as x, y, z points. So I can always have an ordered pair. I always can represent the point as x, y, and z. Z. Okay. Now, associated with the positions x, y, and z, there are unit vectors, okay, that designate the direction x hat, y hat, and z hat. And so what a unit vector is, basically, a position vector indicates where the particle is at a given time respective to origin. Okay, so these are time-dependent vectors, and it will change as the particle moves around. So r, just looking at in a Cartesian coordinate system, r is my my position vector. It's a function of time in general, both equal to the x component at a given time, x hat, y at a given time, y hat, plus z at a given time, z hat. Okay. Now, if I want to look at velocity, velocity is going to be equal to dr dt. Okay. Now I'm going to again use the dot notation because that's just a little more sophisticated. So let's go look at r dot. Okay. That means we have to take the time derivative of everything that's in there, x, x hat, y, y hat, plus z, z hat. Okay. Now, if we look at these terms, notice that I have to use a chain rule. Okay, so let's write down v is going to be equal to, let's expand things out with a chain rule per term. So I'm going to have x, x hat, plus d dt, y, y hat, plus d dt, z, z hat. Okay. Now, x hat, y hat, and z hat do not change with time. So when I do the chain rule, okay, looking at this first term, say I'm going to get d dx dt x hat plus x times dx hat dt. Now, dx x hat doesn't change with time, so that's 0. All right, that will eventually be 0. So same thing for y hat and z hat. So I can rewrite these guys as well. Let me just y dot y hat plus z dot z hat, and just cleaning up what I have here, v is going to be equal to x dot x hat, y dot y hat, plus z dot z hat. Okay. Acceleration is going to be equal to, well, r double dot or v dot, and I can rewrite this as x double dot x hat plus y double dot y hat plus z double hat z hat. Okay, so that's all I have for Cartesian coordinate system. Okay, just writing that up above. So this is Cartesian coordinate system. Okay, sorry. Okay, that's what you learned in engineering physics 1. All right. So now let's take a look at a cylindrical coordinate system. Okay. And again, we have a position vector. Okay, now a point in space in the cylindrical coordinate system is represented by r, and what your book does is your book uses the symbol rho for that. Oops, sorry. Okay, so what we're going to do here, and just let me set something up here. Okay, so what I'm going to do is, the notation I'm going to use is I'm going to use, so to define a point in space in a cylindrical system, I'm going to have rho, and I'm going to have phi, and I'm going to have the coordinate z. Okay, and what is rho? Rho is a position in the xy plane, so I can write this as, if I take the position of vector r and extend it in the xy plane, this is the distance rho. And then phi is the positive angle that I make with respect to the x-axis. And then z is the component along the z direction there. Okay, so a position vector, r, and this is where things get confusing. Position vector in general is denoted by r, and we can write this as, well, rho hat plus z hat. Again, associated with each position, I'm going to have rho hat, phi hat, and z hat. Okay, now what are these guys? Rho hat indicates the direction of the increasing rho. So rho hat is a vector, and was kind of, oops, sorry, let's use this. So if I want to draw this, rho hat would be a unit vector that points out like that. That's rho hat. Okay. What is phi hat? Phi hat is a direction of increasing angle phi. So phi hat would be like that. Okay. And then z hat is in the same direction as we had before. So z hat is a direction like this, in the direction of increasing z. Okay. So those are my components. However, there's a big difference between rho hat, phi hat, and z hat compared to x hat, y hat, and z hat. Okay. Now, notice I have some angle here. If the particle moves, okay, then what's going to happen is, right now rho hat points like this. If the particle kind of rotates around, both rho hat and phi hat will change its direction. Basically, that means that rho hat and phi hat are not constants in time. Z hat is a constant in time. So the real big difference here is that rho hat is a function of time, okay, and phi hat is also a function of time, but z hat is not. So then when we take the time derivatives, okay, to calculate, remember what we want to get is v, and v is going to be equal to that right there, or again d dt of all this stuff here. Okay. Now, for the z hat term, we're going to get z dot z hat times z times the derivative of z hat. Well, z hat doesn't change. Okay. Rho hat does. Okay, and that's so let's write down the next term in calculating the velocity. So I'm going to get rho dot rho hat plus rho hat dot plus, and then here I'm going to get z dot z hat plus, and let me just write it out, z like that. All right, now this term here is 0 because z hat doesn't change, but rho hat does change. All right, now you've seen this before in the context of, think about how vectors can change. Okay, a vector has a direction and a magnitude. Okay, so if the direction changes, then the vector changes. If the magnitude changes, then also, so it can change in two different ways. Okay, and what we could do is we could look at the change. Let's take a look at the change of the position vector at 2 instances of time. Okay, and I kind of have it drawn right here. Okay, so what I show here is I have a position vector at times t1. I have a position vector at times t2, where the difference of the time is delta t, and delta t is just some infinitesimal. We can look at how delta t goes to infinity, or a small infinitesimal thing. Okay. Now here, in order to calculate, and what is delta r? Delta r is the difference between the two. Now if I have these two vectors, I have to subtract them. The difference is going to be perpendicular to the direction of the two. Okay, we've seen this before in engineering physics 1. So I have a very small increment here. So the direction of delta r is, well, first of all, the length of this in time is going to depend on delta phi. The larger delta phi is going to be, the bigger that's going to be. The direction is going to be perpendicular. I can prove that by just taking the two vectors and subtracting them. If I have a really small angle between the two, I subtract them. The difference is going to be perpendicular to the two. All right. So what does that mean? Okay, so now notice, so what I expect is that if those two vectors just say change in direction, I expect the change to be in the phi hat direction. Okay. And so if I take a look at the terms here, okay, this guy here is done. I expect this rho hat term, that is in the direction of delta r that I showed below, and I expect this guy to be in the phi hat direction. Okay. All right, does that make sense? Okay, so so now we can show, okay, so what I expect is when I take the derivative of this term here, I expect that the rate of change of this guy is going to be in the phi hat direction. All right. Now we can show that explicitly by writing rho hat and phi hat in terms of my Cartesian coordinate system. So if you take a look at my diagram here, take a look at rho hat, all right, and maybe it might be better just to draw this in 2 dimensions, okay, in the xy plane. So I'm going to draw here. Let me just make sure I got this guy here. I'm going to draw an xy plane. So this is x, this is y. This is not r but rho, and then this is phi, and then this is rho. So that's basically, I'm breaking that in the plane there. Okay. Now let's draw rho hat and phi hat again. Okay. Rho hat is going to be a little unit vector that points like this, and phi hat is going to be, let me just erase this guy here because it's in my way. Phi hat is going to be a little vector that points like that direction right there. Again, remember this is rho. Okay, so using a little geometry, we can show that rho hat, okay, so this is the direction, is going to be equal to, remember it's a unit vector, so cosine phi x hat plus sine phi y hat. Okay. Phi hat is going to be perpendicular to that, and you can see here it kind of points like this. So here I'm going to see, now here notice that it points in the minus direction for a positive rho x hat, and plus cosine. And, you know, you may say, where does this? This comes from just basically a right triangle, using a little trig to get that. All right. Now, what do we want to do? I mean, really what we want to do is look at rho hat dot. Okay, rho hat dot. Okay. Okay. So let's take a look at that derivative. So I'm going to, again, take the derivative of this. I have to use a chain rule. So I'm going to take the derivative of this. Derivative of cosine is minus sine. But then I have to take, using a chain rule, I have to take the derivative of phi respect to time. So what that's going to give me is going to give me minus sine phi dot. Remember, phi is a function of time. And then x hat, okay, well, that's the constant and doesn't change. Here I'm going to get cosine phi dot y hat. Okay, now I can factor out, okay, a phi dot, and then I get this this bad boy here. that stuff in the parentheses is just, that is rho hat. All right. Sorry about that. Okay. So what do we show? We show that, well, first of all, the derivative, the rate of change of this guy is going to be in that hat direction that I talked about earlier. Okay. So going back, now I can write V completely. V is going to be equal to, what do I have? Rho. Okay. Rho dot rho hat plus rho, now times this thing here. Okay, well that thing there is this. And then finally we have z dot z hat. Okay, so that is an expression for velocity in a cylindrical coordinate system, 3 dimensions. Okay, now remember vectors can change by either the magnitude changing or the direction changing or both. Say I have r, okay, as position vector, and say that all it does is change by changing the length. Okay, well obviously this term here, it depends on rho dot. So if just the length of the vector changes, this thing will change. If just the length of it change, this thing here will not. Okay, and then, well, I'm sorry, I forgot the dot there. That might change too. But you know, going back to my, where did I have it? So if we looked at our system here, if we looked at the system, say just this part changed. Okay, if this thing just got longer, then this term here would change, but this would not. Okay, so this is again this idea of magnitude and direction will change. Okay. All right. So what do we have so far? So what we do is, now we can do is we can, this is my term here that I'm interested in. Okay. And then what we're going to do is just paste this here. Of course, it didn't work. Okay. So what I have here is, now I have my velocity. Oops. And let's get rid of all this stuff here, because that's where I ended up. Okay. So now what we want to do is we want to, well, you know the next step. Next step is to calculate the acceleration in a cylindrical coordinate system. Okay, so A is going to be equal to, well, either we can say it's V dot or R double dot. Okay, so what that means is I have to take the time derivative of all this stuff right here. Oops. Okay. So rho dot rho hat plus rho v dot v hat, okay, plus z dot z hat. Now let me just kind of work through this, okay, a little bit. Look at the first term. I'm going to get rho double dot rho hat. Okay, that's cool. I'm going to get here now rho dot rho hat. Okay, well, at least I know what rho hat is. Here I'm going to get rho dot v hat. Then I'm going to get rho v double dot rho hat. Now I'm going to get rho v dot v hat dot plus z times z double dot z hat. Okay. Now notice I have some new terms here. Okay, so this term makes sense because what that is just the acceleration. So if the vector just changes its direction, its magnitude but not its direction, that's the only term that will affect. Same thing for here. Okay. Now this guy here, well, we already know what rho dot hat is, so we can use the result before. This term here, okay, well, there's nothing, this is a new term. This is a new term here, okay, but something special, okay. This term, so this depends on the rate of change of rho and the angle. This just depends on the rate of change of the angle. So it's basically, this kind of looks like this is an angular speed, or alpha you would maybe call it, times the distance to give me this is the to give me the term there. But the new term we have is this guy here, or more specifically, the row hat dot. Okay. So what we're going to do in class is we're going to compute that. Okay. And what we're going to show, and let me just write down the result. But what we're going to show, actually, I'm not going to write it down. We're going to work on this in class. Okay. So we'll see you there. Take care. Bye bye.